Hello and welcome back. Alright, so today we're going to take a look at the implementation of our Dijkstra's algorithm. Now if you remember in our edge code when I was talking about the diagram, be sure to change this value in 6, or that used to be 6, in your code to 5 so that we get a nice unique answer to our set. The way the Dijkstra algorithm works, it's just going to give you back one of the smallest paths. It doesn't actually store all of the shortest paths if they're the same ones. You'd have to add some special code for that to get that case to work as well. But that's out of the scope of this video. I also want to tell you one more caveat of Dijkstra's algorithm. In order for the algorithm to actually work correctly, you have to have edges that have all non-negative weights. That is, you can't have a path that actually makes it cheaper to go through. So, like for example, between A and B, if that was -1, Dijkstra's algorithm will not, in fact, work for that type of graph layout. So usually we don't have that though. Edge weights are usually always positive anyway, so Dijkstra's algorithm works fairly well for that. Okay, so to get started, let's go ahead and define our function prototype. Actually, so I have the pseudocode copied in my paste buffer, so I'm going to actually put this in our code so that we can reference that as we implement our function. So I just copied this straight out of the Wikipedia article, and so that's what we're going to have as our building block. So let's go ahead and provide the function prototype for Dijkstra's algorithm. So for now, we're going to have a return type of void. We'll fix that later. All right, shortest path, and we know that we're going to be using a graph. This is a class method, so we don't actually have to pass in that graph. We do care about the starting node and the ending node. And for that, that's what we're going to use. Okay, so let's go ahead and look at our pseudocode of what we need. So we know that we're going to need a distance table, a previous table, and we're going to need this queue set. And I told you in the previous video that there's actually already some built-in types that we're going to be leveraging from the STL to do that. That first one is going to be a map. And remember, a map is a key value association where you have a key that you can look up kind of like an array syntax so that it's easy to use and it has some value associated with it. So this first one's going to be called dist. So obviously the value that we're going to be storing over there is going to be an integer, and that's going to be the current distance amount that it takes to travel from the nodes. Okay. Then we're going to need another map. And this one is a previous node list. So we will go ahead and have the value. I spelled that wrong. The value is also going to be a node. So the key is going to be a node, and then we're going to have that previous value also be a node. Okay, so the other item is a set. And a set is just a collection of items. And I believe this set has the semantics of only now allowing unique items. So perfect. The set also allows us to add them in a little bit differently than the vector does at a better performance. Okay, so we have our variables that we're going to be needing to use throughout this algorithm all set up for us. Now let's go ahead and do the initialization stage. All right, so we're going to need this for loop over all of the vertices in our graph. Well, that's pretty straightforward code to write. So we have our edge map, our adjacency list. Where's it at in our code? Our adjacency list right here that we need to search through. Okay, because remember the adjacency list is a map of nodes, and let's actually change that to node. It's a graph of nodes, and all the key values are our nodes in our graph. So we'll just do edge map iterator. Okay, we'll call it IT. That's going to be our adjacency list.begin. All right, while IT does not equal adjacency list.end, iterate that, or increment that iterator. Okay. So now let's go ahead and see what's happening. We're setting the distance to infinity. Okay. We can do that. IT first. Remember, the first item off that iterator gives us our key value. And now we don't actually have an infinity value when we're dealing with integers. So we have a couple options. We can either use some, well, actually we only have one option. We can use some number to represent infinity. We can use negative numbers, or we can use the maximum int value. And that's what I'm actually going to use. Okay, so standard numeric limits. Int max. Okay, so at this point, let's go ahead and add our missing header files too. All right, so standard numeric limits this is actually a standard way to get the maximum value that can be currently represented by the type that you pass in. So in this case, this will give us the max value that can be represented by an integer. And the nice thing about this is that this is portable code, and it'll work everywhere that has an STL implementation. Okay, so up here, we are going to need to include limits, and we will also need to include set. Okay, because we already have map, and limits is the new one we just added. So let's go ahead and build and make sure I haven't broken anything at this point. Perfect. Okay. So that's basically our infinity set. Now we're going to need to have a previous be undefined. So all we really need to do is just add our item, our key, our node that we're looking at into our list, and we don't have to associate any value with it. Okay, so we just do previous IT first. And remember the semantics of the semantics of the map class. If this key doesn't actually exist inside the map, it'll add it for you. Okay, there's one other thing I want to do is I actually want to make this this function right here constant, so that we can actually indeed call this on a constant graph, because this function shouldn't update any of the data within our graph itself. Okay. So, there's one more thing we want to do. And remember, look down at line 6 in our pseudocode. We say Q is the set of all nodes in our graph. Well, in order to build up that set, we should go ahead and do it while we're iterating over all of the nodes to begin with. So let's just do nodes. And we'll do insert and IT first. Okay. Perfect. So now we've added all of our items, we've done all our initialization. The next thing we want to do is we want to set that initial distance to 0. So we don't need to do that in our loop. So let's go ahead and jump out. So dist start equals 0. Okay, and so that actually wraps up all of our initialization code. That covers lines 2 through 6. And now we can actually start doing the real heart of our algorithm. So now we have while Q is not empty. All right, that seems pretty straightforward to do. While Q. So that's our nodes list. While it's not empty, go ahead and do our work. All right, so U is this temporary variable that is going to be the vertex that is the smallest distance within our remaining set of items in Q. Okay, so I'm actually gonna use another STL item to do this basically for us. And let me just go ahead and write this line out first, and then I'll explain what it's doing. Okay, we got the standard min element, nodes.begin, nodes.end, and distance finder, and pass in our distance. Okay, so let's jump up and add this header file that we're going to need, and then I'll explain what this actually does. Okay, so we've included this algorithm header file. Now the standard C++ STL library provides a lot of algorithms for us already. Min element, max element, find items. There's a ton of other ones that it actually provides implementations for, and all we need to do is pass in the specific information, or the specific implementation piece to kind of provide the missing functionality in that list. So, in other words, instead of us writing a for loop that iterates over our nodes list here, what we want to do is so instead of writing that iterates over there and then checks if one of them is less than the next one, storing that temporary value and doing all that stuff, we can actually use this standard min element that will give us that implementation for us. All we need to do is pass in the comparison information. And so since our comparison information is actually based on our distance table, if you remember back from our whiteboarding, let's actually just jump over to the whiteboard. It's based on this table right here. What we want to do is, while it iterates through those nodes, remember that we were pulling that data out of the distance table to figure out the weights in there, or not the weights, but the distances in that table. We want to be able to pass that in so that it can do the same thing. Okay, so what I'm passing in here is I'm actually passing in a class, and this class is going to provide the meat of the functionality for doing that comparison for us. So, and then at the end of this, it's actually going to return, I believe, what does it return? An iterator? Yeah, it returns a pointer to that node, which I believe is through an iterator. So we dereference it, and then we assign that value to our temporary node. So let's go ahead and implement distance finder. All right, I'm going to put this under a protected section because, well, we don't really need this exposed anywhere. And I'm also going to make it a struct, and that's just because I want everything public within it. So it's going to be called distance finder. All right, and we're obviously going to need a constructor. And remember, I was passing in that node set, so it's just going to take a standard map of nodes, and we'll call it nodes. Actually, we'll call it D, because it's actually going to be a distance table. It's a standard map of node int, and we'll call it D. And we're going to create a member variable called dist and initialize that with the value that we pass in. Okay, so let's go ahead and declare that field for us. We'll call it dist. And now this is the actual heart of this functionality that we're going to do. We have to define how the comparison between two nodes that that the min element passes in. So we override this bool operator. All right, it takes in two nodes, and then we return distance A less than distance B. And so the question that this operator is getting called for is, hey, is A less than B? And so we need to provide the logic to determine if node A is indeed considered as less than B. And so what we do is we look up at that table and we find out whether or not that is true. All right, so I hope that made sense. That's kind of an advanced feature, but I want to throw in the way that I think is the proper way to do things, and leveraging the STL as much as possible is usually a good thing. We don't need to re-implement a bunch of different algorithms, kind of like we're doing it for Dijkstra to learn how it actually works, but you wouldn't really implement Dijkstra as if you had a library to call it. You would just say, hey, what's the shortest path on this graph? So let's go ahead and start leveraging that, except for in the cases where we want to learn how the algorithms work. Okay, so and you'll be able to leverage this in all of your problems going forward too. And I find that it's really just, if you're not exposed to it, you don't know those things exist. And so I'd like to expose you to as much of that as possible so that you can go ahead and grab that data and make it useful in your other projects. Okay, so let's go ahead and build and make sure I didn't do anything weird, which I did. And that's because this should actually be a constant iterator. Okay. And then we have an unused variable u, and that's just a warning because we haven't used u yet. And so that'll go away after we actually start making use of it. Okay, so we jump up into our pseudocode. So we have line 8, which actually is a line that is hiding a lot of detail of what the implementation is going to look like. And so pseudocode, sometimes it does that. There's actually a lot that goes into implementing line 8. Okay, so line 9 and 10, those are trivial. If our distance of u equals our, what we're calling infinity, this guy right here, then break. That's pretty easy. All right. Now here is where I actually want to add in our optimization. If we look up on our pseudocode, line 11 is just remove the u from q, search all of the neighbors around there that haven't been visited yet, and then do all of our work. But at this point, if we've actually reached our ending node, then we know the shortest path between the start and the end. So we don't need to compute the rest of the values. So what we're going to do is if u equals our end node, we're done. Okay? Let's go ahead and break out of this loop. Okay, so now let's go ahead and continue back to our pseudocode here, because regardless of whether or not we had this optimization, it's not always going to be the case that you find that first ending node. Okay, so what we need to do is we need to remove u from the nodes list. All right, to do that, we just simply call the erase function off of nodes, and that erases that node from the list. And then what we want to do is we want to start iterating over all of our adjacency list items. So I'm actually going to create a temporary variable because it's kind of a long line of code, and since the iterator syntax is the iterator.begin and the iterator.end again, instead of having to write that all out, I'm going to do it a shorter line. So constant standard vector edge pointer, because remember we're just trying to get all the edges adjacent to our list. We can find u second. So what this does is, hey, so what I could have done, what we've normally seen is doing this syntax, this array syntax of pulling back or pulling out information from the adjacency list. Now the caveat here is we've actually marked this function as being constant, so that means we can't modify any of our members within this class. And if we remember, the semantics of this map class is if this key does not exist, one gets added for you into the list. So that means we're going to that we always have the potential of modifying our adjacency list. So in order to make this function actually work as a const function, we need to use the find method. And so what that does is it returns back an iterator of the item that it found. Okay, and so then we call the second to get the value, which are the edge pointers. Now it is possible that our list, if for some reason didn't have this u in here, this would actually give us the end iterator, and we'd end up with an error in our code right here. So we could guard against that, but our implementation, we know that the edges are always in there. So if they're not in there, or sorry, if the node's not in there, then we have a bug in our code, and so we should never actually hit that case. Oh, okay. So this gives us back all of the edges that are adjacent to the node u. Okay, so let's go ahead and iterate over those edges. So for standard vector edge star iterator, we'll call this it. Oh, this should be a const iterator. Sorry. Edges.begin, and then while it does not equal edges.end, increment our iterator. Alright, so this is what, right here, This way, that's why we did this variable up here, so I wouldn't have to actually write all that in this already long line of code. Okay, so let's jump up into our algorithm and see what's going on. Okay, we have our for loop. We're ready to jump over all of those edges that are actually still available for us to look at. So we are going to do int. We could call it alt, but I'm going to do d. Doesn't matter. Distance of u. Okay. And then we're going to add in the iterator's weight. So the edge, we need to get the weight of the edge. So we need to dereference the iterator. That gives us an edge pointer. Then we need to dereference the edge pointer and get the field weight. Okay. Alrighty. You know what? We actually have a bug in this code right now. Line 12 actually shouldn't look at any things that have not been added, or sorry, which don't exist in Q. And currently we're actually looking at all of the edges, the nodes that exist there. And so what we want to do is, let's do a check here. If our star, if nodes.find star it target, okay, that's our node. If that equals nodes.end, then don't break, but continue this loop. So just skip that edge, because we don't actually want to evaluate any edges that point to a node that don't exist in our list. We could end up with some problems there in certain circumstances. Okay, so that covers that kind of hidden comment implementation piece. All right, so now we do if d distance u equals our weight. All right, so that's this right here. Distance u, the distance between u and v, that's the weight field that we have. Okay, then we just simply ask the question, if distance of v, which is our target node here, so star it. Actually, let's just go ahead and do this, since we're going to use this in a couple places. All right. V and v. Okay. If d is less than the distance for v, then we're going to go ahead and set distance v equal to d, and then set our previous v equal to u. And it's really as simple as that. So if we build, everything should be happy, perfect. Now you're probably noticing that, we did all this work to find the shortest path, but we didn't actually return any information back to the user. So let's go ahead and return back the information for the shortest path. All right. So we'll create a standard vector. It's just going to be a vector of nodes, and it's going to be the path. Okay. And so what we want to do is we want to go through that previous table and populate back out our answer. So let me jump over to the whiteboard. So we're going to start at D. We want to have the vector that we return back have D, B, and A in it. Okay. So in order to do that, what we do is for node n equals end, while n does not equal the start, so basically we're gonna jump through that table, populating our answer. So we do path.pushback n, and we set n equal to previous of n. All right, so what we have here is a reverse order list of the shortest distance from A to D. Okay, and now if we simply just return path, we can actually go ahead and do some information with, or do some. We can do some output of what this shortest path is going to be. So let's go ahead and return a vector node. Okay, so down here, standard vector. Now we need to do graph :node because this type def is actually defined within the graph scope. Okay, so path equals g period shortest path. Oops, and we want it from A to D. Okay, so now this is going to give us the path in reverse order. So what we actually want to do is we want to output that data in reverse order. So we don't want the answer to be DBA. We want the answer to be ABD. Okay, so let's go ahead and do that. So we're going to create a vector graph node iterator. Reverse iterator. So this is an iterator that's going to go backwards. This is in a for loop. Duh. For iterator, we'll call it IT, equals path.rbegin. And rbegin is a short way, or it's the way to get the iterator for the vector that starts at the end and goes toward the front of it. I hope that made sense. While iterator is not equal path.rend, and then increment the iterator. Okay, so let's go ahead and just see out our answer here. Okay. Let's build. Let's bring up the console window. We'll clear that out and run it. Okay, so you'll notice that we have a couple things missing. Our shortest answer, or our shortest path from B to D is B to D to A. When that just looks completely wrong. So let's go look and see what we got. So if we look at what we're returning, we forgot to actually add the start to our list. So we'll do path.pushback A, which is our starting point. Okay, so now if we go return it, okay, now we have A to B to D. All right, that actually looks a lot better. That looks like the shortest path between A to B to D. Now, let's just go ahead and fix the formatting a little bit. I don't want this ending arrow to be here. So what we're going to do is we're going to get rid of that. All right, so if the iterator plus 1 does not equal path.rend, so if where the iterator is pointing to, if we move one more step, is that the last entry? If it is, then we don't want to output this arrow. Otherwise we do. Okay, we build, oops, we run, much better. We got A, B, and D. Now there's one more piece of information that we're going to want to have, right? We want to actually know what the weight of this path is. And so there's a couple ways that we can do this. We can add more information to the return type of our path, or we can pass in a parameter here that will actually calculate it'll actually store the value for us. Okay, so I'm actually going to do it that way. I'm going to pass in int weight. I'm going to initialize this to 0. And then I'm going to pass in the address of weight. Now in our function, what I'm going to do is I'm actually going to pass in an int pointer. Int star weight. And by default, I'm going to set this to the value of null. So what I'm doing is I'm creating an optional parameter. Depending on what coding guidelines you want to follow, this may or may not be a recommended practice. I like the optional parameters because I don't have to create a bunch of different function signatures, but they can be confusing and they can be a little bit subtle. So just be aware of that. But what we're going to do here is we're going to pass in a pointer to weight, and then we're going to change the weight value based on what's calculated for that distance. Okay. So right here, before we return path, what we actually want to do is we also want to set that weight. So we do want to check though. If weight is null, we don't want to do anything. So if weight is not null, that means we've actually been given an address of a value place in a valid place in memory where we can write data to. So if it's not null, well, that's our assumption. If it's not null, let's go ahead and set the path. The distance to that in there. And so we're going to dereference weight, and then we're going to set the distance to our end, and that's actually going to give us that total distance between the path. Okay, so let's actually go ahead and see if we broke this without passing in weight. All right, that's just an unused warning. That's fine. Okay, perfect. No crashes. Nothing funky happened. Now let's pass in weight, and let's actually output that at the end. Okay. So if weight, let's actually initialize this to -1, and that'll be our error case. Or we can use that infinity value we've been using too. Let's go ahead and do that, just to keep things consistent. All right. If weight does not equal our infinity value, go ahead and output our weight. Weight is that. And at the end of all this, let's go ahead and, for good measure, add an end line. Okay. So if we rerun it now, hey, we can see that our weight is actually reported back to us as a value, and we get A, B, D, and the weight is 6. So now the reason why I passed weight in as an optional parameter is that the most important piece of this functionality is finding that path. Only sometimes do we actually care what that weight value is. And so I don't want to have to make the users always parse the result, the end data, to get the path value and also the weight value. If they want the weight, I want them to be able to pass that in, pass a pointer to a location, and I'll set that weight for them. But the main core functionality of this function is to actually find our path. Most of the times we don't actually care what that weight value ended up being. That's kind of a not an implementation detail, but it's kind of a smaller detail that doesn't necessarily provide us much value. Now, obviously, if we're getting directions and we're passing, we want that weight information back so we can guesstimate how long it's going to take you to get there. But yeah, so it's kind of a piece of information that may or may not be useful. And depending on your algorithm, you may actually want to return both the path and the weight together as one single return type. But that's up to you. So that is our implementation of Dijkstra's algorithm. I know this video went long and we kind of sped through a lot of the code, but be sure to go over this code and understand each of the intricate parts, especially the using of the STL libraries, min element. Go do a little more research on those. Maps and sets, those are pretty straightforward data types. I don't think we've talked about them, but they're fairly trivial to understand at least what's happening with them. So that is our code, and I hope you enjoyed Dijkstra's algorithm. Thanks.